Okay, so now that we understand complex numbers, we can talk about a pretty cool application of them that is made much easier with shaders. So let's consider this equation. So let's say we start with an initial complex number, we'll call it z0. And then we have a constant c, which is also a complex number. So what we'll do is we'll multiply the initial complex number by itself, and we'll add c, and we'll get the complex number z1. Then we can take z1, multiply that by itself, and add c, and get a number z2. And we could take z2, multiply itself by it, and then add c and get c3, and so on and so forth, until eventually we'll get to some complex number where if we square it and we add c, then the magnitude of zn plus 1 is greater than some constant called the escape value. So what we want to see is these are complex numbers can be thought of as vectors. As we keep doing this complex multiplication by itself and adding some constant vector, this thing's going to be scaling and rotating and moving along some path. We want to know how long does it take for that thing to escape a particular radius or particular distance from the origin. And if we color the point, the starting point, z0, on a canvas with a color that's proportional to how long, how many iterations it takes to escape, we get this crazy pattern called Julia sets. So here I can choose a different escape value. So here's what it is if it's 3. I had it at 2. And these are just variables for how I'm coloring it. But if I move around, I can zoom in and I see that, okay, so all the points that are drawn white are points that never escape within some, I think after 100 iterations, they still don't escape. But all the other points that have a non-white color will escape at some point. The darker they are, the longer it takes them to escape. The lighter they are, the more quickly they escape. So it kind of makes sense. If I start further away from the origin, it makes sense that I'll escape more quickly. But the really fascinating thing is if I zoom in on this, I see copies of the same shape repeated. And within them, I have copies of the shape that are repeated. And within them, I have copies of the shape. So it's this infinite shape that's made up of itself. So many copies of itself. And so we call that a fractal. So if I can take a shape and say this shape is defined as itself rotated and scaled and translated. So here I've got a copy, here I've got a copy, here I've got a copy. Then we can recursively say, well, that one's made up a bunch of copies of itself, and we can keep going. Now in GLSL, eventually we'll lose some precision. We don't have enough precision to go any further than this. But mathematically, we can actually go infinitely. So it's crazy that the amount of time it takes the points to escape, when plotted, actually makes this fractal pattern. But the code to accomplish that is actually quite simple. So what we do is we'll start with a vec2, which is just going to be our initial point. And I could just say it's directly equal to that varying position that comes through to the fragment shader. But I also have two uniforms that are related to where my mouse is, so I can scroll around and zoom in. So U scale is how much I'm zoomed in, and U center is where I'm centered on my canvas. So what I have to do is keep track of how long does it take to escape. And so what I'll do is, these are temporary variables to help me as I go, but I'll have a loop that goes through up to some maximum number of iterations. If I haven't escaped by then, I'll just color it white. And then I go by 1 each time. And then I just implement complex multiplication. So I say, okay, my new x component is zx times zx minus zy times zy. So you see that that's the real component of complex multiplication of my z by itself. And then I say y is equal to 2 times zx zy. And that's the imaginary component of z times itself. And then to both of them, I add that constant, so this is uniform, that constant c. So this is the real component of c, this is the imaginary component of c. Now I check to see, is the magnitude of z greater than my escape radius? And so alternatively I can say, is the dot product of z with itself greater than that amount squared? If so, I say, okay, it took me that long to escape, now I'm done, I'm going to break. Now this is one place where you really can use break because, as I said before, for loops require it to be known at compilation time how many iterations they're going to go through. So I have to set up this loop to go through a maximum number of iterations. There are no while loops in GLSL. I can't say while it has escaped, keep going. I have to say try up to some maximum number of iterations. If you've escaped, then just break out a loop. Otherwise, update z and keep going. But then when I get down here, I can use that number count to come up with a color. So there's a formula I have to come up with a color. And so really what you see is what has a large impact on the shape that you get is this constant that you add each time. If I make the constant 0, so here's the constant, -1. So actually the constant was just -1 to start with. If I make the constant 0 plus 0i, I end up just getting, oops, hang on. Well, let's try 1 plus I, just a different one here. I think there may be an error with how I'm updating this here. Hang on. Okay, let me just try 1 plus I instead. Well, that didn't work either. Oh well, I'll fix that and we'll look at it tomorrow. But yeah, C has a big impact on the final answer here. But anyway, so that's how it works. So study this code. It's just a couple weird things, like I have to loop up to the maximum number of iterations no matter what. And I also, because count is going to be in an equation that has floats in it. So these are going to be floats at the end. And I'm setting count to be I, then I also needs to be a float. So I kind of have my hands tied behind my back as I'm coding this thing. All the types have to match exactly, and I have to loop a constant number of times for each pixel. But if I do that, I get this beautiful shape, and it happens very quickly. At interactive rates, I can scroll around and zoom in. If you tried to do this just in JavaScript, it would probably take a few seconds just to render one frame. So that's why this is very neat. And so this is a warm-up for the exercise that you'll be doing in the homework, which is Newton fractals. So this is another way to do something with complex numbers that allows you to get these fractals. So anyway, we will talk about that tomorrow.